All right, that's fine. Please, continue posting any questions that you have as we go along. But I'm going to talk a little bit about some of the kind of cutting edge quantum applications that IBM's featuring. I may give a couple last minute pointers for people for the hackathon. I'm one of the judges for that, as is Dr. Yu-Ji Lee. We have another person here, Dr. Chen, who's also interested in quantum, that'll be judging that. And we'll be going around and visiting people's, posters and seeing what they have to say. Um, let's start with just talking about some of these applications. So we're taking a broader look at some of these near-term applications, and we're going to talk about, what the suitability is for a quantum computer for certain styles of work. Quantum complexity classes. Oftentimes we hear people talk about P versus NP. Okay, so there's problems that are solvable in polynomial time, and there's problems that are verifiable in polynomial time. Then we have NP complete, which is like the hardest class of problems. These are problems that have that factorial complexity. But in quantum computing, we have to define our own new methods of defining these things. So there's BPP, which is probabilistic classical polynomial time problems. Then there's BQP, which is the quantum equivalent of BPP. These are solvable on a quantum computer with a bounded error. So this isn't deterministic necessarily, but that these can be solved on a quantum computer and within a certain error bound. And that's the kind of class that we're really targeting with quantum computation many times. All of these classes exist within probability space, but BQP doesn't necessarily overlap with NP complete. And the issue is the P versus NP and the NP complete. The mathematical proofs for which problem belongs to which class aren't well developed. There's a few mathematically proven quantum speedups, like Shor's and Grover's, where we're like undeniably quantum computing will be faster than this. But one is like these mathematical proofs are hard to do. They're hard to configure. And a lot of times I think that we're more likely to find solutions from a bottom-up solution as opposed to that top-down from the mathematical proof of investigating what types of problems we can solve or attempting to solve problems on quantum computing, and then allowing us to mathematically verify or validate or prove after the fact. There may be exceptions here, but it seems that we should try to solve these problems with the hardware that we have, with the equipment that we have, instead of just completely proving that these problems can be solved faster, that a quantum computer will be faster. And there's always this interplay going back and forth of the quantum computing versus the classical computing, where someone will try to prove a speed up on a quantum computer and then a classical algorithm will outpace that. So it's the algorithmic development still ongoing. There's a few proven quantum speedups. And when I say proven, I don't mean demonstrated. I mean, like, mathematically, you can't go faster than this. Now, there's lots of demonstrated quantum speedups, and we're going to talk about some of those today. But generally, we're going to go through these heuristic solutions, okay? Instead of deterministically prove, this is the actual final answer. Still, even if we're not getting optimal solutions, the best global solution, these non-optimal methods are valuable. All right, a 0.1% improvement in $1 million, or $1 billion investment portfolio is, tens of thousands, hundreds of thousands of dollars over time. So we can use quantum to try to speed up our heuristic search with classical methods. So we're trying to target this sweet spot where classical computing is not enough, and we have the existing hardware today. So, we're limited on qubits. With IBM, I think the most qubits we have access to is 156. We're shallow on circuit depth because we have to apply that error mitigation. We don't have true error correction yet. People are projecting for the early 2030s. But still, the focus today needs to be on error mitigation and suppression, scalable experiments, and making a path to future quantum advantage. That is like proving things with toy models, demonstrating that, hey, whenever we have a quantum computer with 5,000 qubits, 10,000 qubits, whatever the case is, we can solve the real world example of this problem. So it's trying to solve problems today with what we have, or at the very least, showing the path to how this will apply in the future. There's 3 areas where quantum computing is really excelling at the moment. All right, there's nature simulations. So this is like the quantum chemistry type stuff we've talked about, the material science. That is that we're able to represent the state of a system in the quantum computer and calculate like ground state energies or things like that that are just intractable on classical computers. And it makes sense that a quantum computer is going to be better able to capture these quantum effects that are occurring that we have interest in based on how they're going to affect this drug that we're designing or this new material that we're trying to build or things like that. And some key aspects of that is like VQE or sample-based quantum diagonalization. Then optimization type problems, these problems that have to do with combinatorics that can be finance, industrial design, logistics, think like Amazon routing, trying to solve, what's the best route that these vehicles can take to save gas, and what else. And then quantum machine learning, and this, there's a lot here. Many of the hackathon projects are largely dealing with quantum machine learning. There's quantum neural networks, there's quantum graph adversarial networks, support vector machines, there's quantum kernels. There are these hybrid neural networks where we have a traditional deep neural network and then we have a quantum layer buried somewhere in the middle or at the beginning or at the end where it is extracting some nonlinear feature for us to work with. So these are like the 3 key domains that we're seeing a lot of progress in. And it's IBM has these quantum working groups, and I highly recommend, if you have time, to take a look at what some of these working groups are doing. They kind of have them grouped by topic based on what they're gaining traction on. I know I've seen a lot of stuff out of Oak Ridge National Laboratory, working both with the high energy physics side, stuff like the Large Hadron Collider, as well as with the material science side of engineering materials or evaluating the properties of materials. In healthcare and life sciences, Cleveland Clinic's been working a lot with protein folding. They don't have it on here, but I know Moderna is working with the folding of mRNA. There's the true high energy physics side. Then optimization, I know Los Alamos is working a lot with trying to find ways of solving these interesting mathematical problems. There's a lot of interest from, finance companies. I've seen job openings from Visa for a quantum computing group. And then I don't know a lot about it, but there's a new sustainability group that's working on trying to solve all kinds of problems related to whether that's green energy or environmental, topics. And so it's kind of a less of a domain specific, like we're worried about things that have impact on the environment, but more on how do all these different methods contribute. Hey, if we're optimizing routes for shipping, we're reducing carbon impact. If we can better, make a material that's more biodegradable or that doesn't contain this compound that's toxic. So it's kind of a larger group. Now, I'm not going to go too deep into physics or chemistry or anything here, but there the who's this by? I remember I had this somewhere. I'm sorry. I'll link the paper later. But at the same time, trying to simulate hadron dynamics. All right, and hadron's just a particular uh, type of particle and how they operate in space, and better understandings of electromagnetism and matter, are what drive so many of the advances that we've made in the last 100 years. If you're going to characterize what we've done in the last 100 years, it'd be mastering electromagnetism and particles. And so if we can better understand that, we can make better tools, better equipment, have better understanding of the universe and how those things operate. um, what's interesting with this is just the potential for speed up this has. Simulating these large hadron dynamics, um, like, is just so expensive classically, and being able to simulate these using only 112 qubits and being able to get competitive results is really interesting. Um, Also, these icing spin, okay, this has a lot of potentials for better understanding more on the physics sides. Um, they're using 127 qubits and showing improved performance. And you can see on the IonQ device, their performance between the ideal simulation and the actual run. So, they brute forced this ideal simulation and were able to do this run. And I want to think they, were able to calculate it in roughly minutes. So it's really impressive. And we're seeing how we're driving these real runs of this equipment towards these ideal simulations and being able to actually calculate these things much, much quicker. And then this Moderna with calculating mitochondrial RNA secondary structure prediction. RNA encodes proteins, and if we can better understand which section of RNA is encoding which protein, that's a huge potential for the drugs that we can develop, for our understanding of why certain diseases occur. Many debilitating diseases that affect people are due to some type of protein folding thing, and we don't understand all of them. And so this is a true path forward. And this is only using 80 qubits to accurately match this classical solver, but with that reduced calculation time. There's that. If you watch the IBM blog, they constantly have their use cases of people that are demonstrating this stuff. And, if you go in Google Scholar and, pick a domain and type quantum computing, it's amazing, really, all the things out there that people are finding to do with them. And I've gotten some questions from numerous people, and oh, what should I do? And it's like, well, what are you interested in? Start doing some reading, start thinking about how you could formulate this as a quantum problem, and dig in. It's my background's graph theory, kind of more on the mathematical side and stuff, and I, I have a long commute every day, and I just sit there and think about what kinds of problems I could solve with quantum computing, and it's I have more ideas than I have time to implement. But yeah, a little bit of a pivot. Let's say for those who are participating in the hackathon, please sometime today practice your elevator pitch. 2 or 3 times where the points you're going to hit. Hi, my name is this. My project is named, weaving underwater baskets. Hit them with a problem statement. We don't have enough underwater basket weavers. Give your thesis statement that is like, and we're going to demonstrate how we're solving this using method XYZ. Give any more background that you need to. Talk about how your method works. Hit the results. And thank them for their time and send them out with your message of that, like, hey, we're showing a great way to demonstrate our methods. A great way to demonstrate how these things work. Another aspect is that the judges for the hackathon, we all understand that many of you are brand new to quantum computing or relatively new to quantum computing. So be honest, like, please send us away with your impact and things like that, but be careful before making big claims, with this because, you know, it's I know Dr. Chin's very, you know, versed in this. I'm aware, and so tell us what you did. It's cool. It's cool that you've done it, but also we understand that this is an initial project. So, you know, send us with your message. Tell us why it's cool. Tell us the impact this can have. But please be careful not to overinflate what you're doing. Um, yeah. So, does anybody have anything they'd like to ask, like to know about? We have one more session today. I could prepare something for that if there's a specific topic people are interested in.
Hey Luke, there's something that we've talked about before. I think that talking about how you approach a quantum problem where there's no easy to find solutions for and how you approach those kinds of situations, especially with, Qiskit 2 being up and a lot of the examples that you may be looking at are Qiskit 1. I think maybe just talking about your personal experiences and your methodology for approaching a problem that, maybe someone hasn't been working on, there's not much information.
Yeah.
That's something I think would be a cool thing to go over the last session.
Okay. You know, and I think I'm gonna split that. I'll make a presentation on like my methodology, and it's the stuff that people in my class have heard a lot. Where hey, you start with a problem, you make a toy model of how you represent that, and you know, you test the toy model, you test it with noise, and you scale up with like deploying to hardware being halfway or further through the process. And oftentimes too, the biggest hurdle is twofold. Whenever we talked about all the variational quantum circuits, there's always two parts. There's encoding your features, and then there's developing your ansatz, the part that's, you know, you're solving the problem with. But they're both equally as important. It's not always perfectly clear how we should, you know, encode our data. You know, should we be using registers of qubits to represent one data point? Should we have, you know, there's a lot of representation methods. Um, the utility quantum computing course has an entire lesson on that. That's really good. Let's see here, BAP. Learning. View all courses. Is it? I think it's quantum computing in practice. Mapping. Yeah, so they have an entire section here where we're talking about how to map a problem to a quantum circuit, understanding how we're encoding these things, so that, you know, that's a huge part of what quantum computing is. And it's all the time I have people come up to me and they look at me and they're like, oh, hey, I'm working on this, could I solve it with a quantum computer? You know, and it's a little disheartening, but you know, I always have to look at them and say, I don't know, maybe. You know, because we have to take a look at like, okay, how are we going to encode this? How can we solve this with a quantum computer? Is there an existing algorithm out there that I can just plug and play and test, or do I need to like build a bespoke quantum circuit to represent these features? You know, and I've tried to give everyone a very broad introduction to quantum computing over the last week. I'm covering a lot of different topics. I'm, you know, covering error correction and quantum chemistry and quantum machine learning, you know, and all these different things. But, you know, it's still going to take some time to dig in and really understand how do we encode these features into a quantum circuit? What are we solving here? Hey, should I use an estimator or a sampler? How many shots should I run? What kind of optimizer should I use? So it can be a little challenging. In the next session, we're going to talk about some of the what now. I'll be talking about joining QZA, being part of the Quantum Innovation Center, as well as like learning resources. John Preskill's lecture notes, Ronald DeWolf's lecture notes, the IBM Quantum Learning Platform. There's a lot of stuff out there, and I'm hoping this is the start of many of y'all's quantum journey. But for the 2 o'clock session, I'll I'll kind of demonstrate how I recommend experimenting with quantum computing and trying to determine if this is a problem that you can solve using quantum computers. It's a lot of, okay, hey, we have a couple different ways that we can try to represent this. Let's make a toy model. Let's get that toy model working. Once we have the toy model working, okay, we're going to scale it up a little bit. We're going to simulate. We're going to add some noise. We're going to add some error correction after we've added the noise, and you like are continually iterating and scaling up as you're trying to solve your problem. And oftentimes too, it's I've worked with people and they make their toy model and they're like, oh, it's not better than the classical solver yet. Do you think we should do it? And it's like, well, yeah, but this is a toy model. We can see that, hey, we're getting a reasonable answer out, something, better than random guessing. And so then we start optimizing and building this up to make this circuit more expressive, to have a better optimizer, to play with different encoding methods, to understand what's the best way to do that, that experimental methodology. Anybody else? All right, guys. Thanks for coming out. At 1 o'clock, I'm going to try to point everyone towards next steps. Where to go from here now that you've attended Kiskit Fall Fest, you have an interest in quantum computing. What do we want to do next? And then at the 2 o'clock session, I'm going to kind of give an example of building out, a workflow on. You have a problem that you want to solve. How should we go about, solving that problem and scaling up? Yeah, all right. So guys, I really appreciate it. Y'all have a great day. See y'all at 1.